I know I haven't offered you nearly enough time here to finish this up, but I want to jump in and get started because we do have a lot to cover today. First thing I want to mention is we're at that point in the semester, we're coming down the home stretch. So I want to offer my end of the semester homework and quiz amnesty. If there are any quizzes or homework in my math lab that you haven't finished, please feel free to let me know. Tell me which ones they are. It's really a struggle for me to look through the system and see which ones you're missing. It's just really not a great display, and I can't just pull up the missing assignments. But let me know what homework and quiz numbers you're missing that you would like to redo. And to actually, the homework you can redo without me having to open it for you. It'll just tell you that it's going to take off half the points. The quizzes, I have to reopen for you, so let me know what quiz numbers. But if you've completed anything that's late, please also let me know so that I can make sure I transfer it into the Blackboard gradebook so it's part of your official grade. A good idea to double check, by the way, just to make sure everything has been transferred correctly, because I do have to manually transfer the grades from my math lab to Blackboard, and I'm not perfect. It has been known to happen that I transfer something incorrectly. So please feel free to check that over and let me know if there's anything that you don't think got transferred correctly or if you have questions. Okay, so anyway, on last week on Monday, we talked about rotation of axes. This was the reason we had to go back and do some trig so that we could handle this. Rotation of axes is just due to this xy term in our standard form of a conic equation. So the first thing I'm going to do here is I want to know what type of conic this is. Is it a circle? Is it a hyperbola, ellipse, or parabola? Now, obviously, circle wouldn't matter because a circle rotated is still a circle. But remember, the term was the same as the discriminant for a quadratic equation. It's b squared minus 4ac. So a here is the 7. B is the negative 6 times the square root of 3, and C is the 13. A is always the x squared coefficient, B is always the xy coefficient, and C is the y squared coefficient. So we have negative 6 times the square root of 3 squared minus 4 times 7 times 13. Now this negative 6 times the square root of 3 squared, we can take each piece separately and then multiply them together. Negative 6 squared is a positive 36. Square root of 3 squared is 3. 36 times 3 is 108. Minus 4 times 7 times 13. It's 364. Now we don't care exactly what that number is. What we care is that it's negative. And if that's less than 0, we know this is going to be an ellipse or a circle. Most likely an ellipse because the coefficients on the x and y are different. So now let's go ahead and find our angle of rotation. That's the next thing we need to do. Actually, I probably can leave that in there for now. Angle of rotation is found. The cotangent of 2 theta is equal to a minus c over b. Well, a here we said was 7. C is 13. B is negative 6 square roots of 3. Well, if we look at that, 7 minus 13 is a negative 6 over negative 6 square root of 3. The negative 6 cancel out. We got 1 over the square root of 3. So that's giving us that the cotangent of 2 theta is 1 over the square root of 3. Now, because of the reciprocal relationship between cotangent and tangent, that's telling us that the tangent of 2 theta is just the square root of 3. Now, the reason we use cotangent instead of tangent is in case the a and c terms are equal. If they're equal, we'd subtract to get 0. If it was tangent, we would have a denominator of 0 and it would be impossible. But for cotangent, we can work with a numerator of 0. So let's do the inverse tangent of the square root of 3. So the inverse tangent of the square root of 3 is 60 degrees. So 2 theta equals 60 degrees, which means that theta, when we divide by 2, is just 30 degrees. So 30 degrees is our angle of rotation. Now, what we're most concerned about is sine of theta and cosine of theta. Sine of 30 degrees is just 1/2. Cosine of 30 degrees is the square root of 3 over 2. Now we can go ahead and find our substitution. We know that x prime here, or sorry, that x is going to get substituted with x prime cosine theta minus y prime sine theta, and that y is going to get substituted with y prime sine theta plus, I'm sorry, x prime sine theta plus y prime cosine theta. So let's complete that substitution. Cosine of theta is the square root of 3 over 2, so it's the square root of 3 over 2 times x prime, minus sine theta is 1/2, so it's 1/2 times y prime. Over here, y equals x prime sine theta, well, that's 1/2 x prime. Y prime cosine theta is the square root of 3 over 2 y prime. So some things that we're going to need in order to substitute into this equation. First thing we're going to need is we're going to need to find out what x squared is. X squared is going to be this substitution here squared. So if we multiply that out, square root of 3 over 2 squared is just 3/4. So that's going to be 3/4. Back here. 3/4 x prime squared. Then our middle term, we multiply those together, square root of 3 over 4 negative times 2, so square root of 3 over 2 x prime y prime. Then our final term is this one squared, so that's positive 1/4 y prime squared. So that is x squared. We also need to find xy. Well, that's going to be x square root of 3 over 2 x prime minus 1/2 y prime times y. 1/2 x prime plus the square root of 3 over 2 y prime. So we'll multiply this out. Square root of 3 over 2 times 1/2 x is the square root of 3 over 4 x prime squared. Square root of 3 over 2x times the square root of 3 over 2y is 3/4 x prime y prime. And negative 1/2 times positive 1/2 is a negative 1/4 x prime y prime. And negative 1/2 times negative square root of 3 over 2 y prime is a negative square root of 3 over 4 y prime squared. Combining middle terms here, we got the square root of 3 over 4 x prime squared. 3/4 and negative 1/4 is 1/2 x prime y prime, and negative square root of 3 over 4 y prime squared. That is xy. And then we need to do y squared. Y squared is going to be 1/2 x prime plus square root of 3 over 2y prime squared. Making sure I got the right one there. Yep. So as we square that out, 1/2 squared is just 1/4 x prime squared. 1/2 times the square root of 3 over 2 is square root of 3 over 4. Of course, times 2 makes it the square root of 3 over 2. So plus the square root of 3 over 2, x prime y prime. And finally, the square root of 3 over 2 squared is 3/4 y prime squared. That is y squared. So now we do the substitutions. Now remember the original equation, 7x squared times 6 square root of 3xy plus 13y squared minus 16 equals 0. So we will replace x squared with 3/4 x prime squared. It's going to be a lot of scrolling, sorry about that. 3/4 x prime squared minus square root of 3 over 2 x prime y prime plus 1/2, is it 1/2 or 1/4? 1/4 of that. 1/4 y prime squared. Minus 6 times the square root of 3 times xy, which is right here, square root of 3 over 4 x prime squared plus 1/2 x prime y prime minus square root of 3 over 4 y prime squared. Then, of course, plus 13 y squared, where y squared is that 1/4 x prime squared plus square root of 3 over 2 x prime y prime plus 3/4 y prime squared. And of course, minus 16 equals 0. I'm going to do some calculations right within this here. I'm going to multiply by the 7. This is going to be 21 over 4 x prime squared minus 7 square roots of 3 over 2 x prime y prime plus 7/4 y prime squared. Multiplying here, negative 6 times the square root of 3 times the square root of 3 over 4. That's a negative 18/4. Now I'm going to leave it as fourths because it seems like 4 appears to be my common denominator here. So that is negative 18/4 x prime squared times the 1/2 there. That's going to be a negative, well, I'm just going to write it as a negative 6 root 3 over 2 for now, x prime y prime. And then minus negative 6 times the square root of 3 over 4, again, is a positive because that was a negative root 3 over 4. 18 over 4 y prime squared. Down here, 13 times the 1/4 x squared is 13/4 x prime squared. 13 times the square root of 3 over 2. 13 square roots of 3 over 2 x prime y prime. 13 times 3 is 39/4 y prime squared. And I'm going to add 16 to both sides. So this is going to be equal to 16 now. So let's combine. We have the x squareds. We got 21/4 minus 18/4 plus 13/4. So 21 minus 18 is 3 plus 13 is 16/4, otherwise known as 4 x prime squared. Let's look at the xy term here. This one hopefully will disappear on us. So we've got negative 7 and negative 6 is negative 13 square roots of 3 plus 13 square roots of 3. It does cancel out, which is good. That's what we were hoping for. the y prime term, or y squared, I should say, y prime squared, 7/4, 18/4, and 39/4. So that's what, 25/4, 64/4, otherwise known as 16. So we have 4x prime squared plus 16y prime squared equals 16. So 4x prime squared plus 16y prime squared equals 16. And as always, we have to get rid of this term, has to become equal to 1. If it's a parabola, is the only time we don't need that, or parabola or circle is the only time we don't need that equal to 1. For a hyperbola or ellipse, we have to make that equal to 1. So since we know this is going to be an ellipse or a circle, we have to make that equal 1 for the ellipse. If it were a circle, these coefficients would have to be the same, and they're not. So we're going to divide by 16 to make that equal 1, so which means we divide each piece on this side by 16. 4 over 16 is 1/4, so this is x prime squared over 4. 16 over 16 is 1. So I'm going to write this as y prime squared over 1 equals 1. And now we could graph. So our center is at 0, 0. X prime squared over 4 means in the x direction, the square root of 4 is 2. So that means we go 2 units in the x direction. The y prime squared over 1, the square root of 1 is 1, which means we go 1 unit in the y direction. There is our ellipse in the non-rotated form. Okay, so as I said, that's something that I'm not going to push real hard. It's not a horrible thing, but it's a lot of manipulating symbols and a lot of chances for errors there. Even in myself, I'd say about 1 in every 3 of those problems, I make a major mistake and have to go back and fix it just because there's so much algebra going on. So today we're going to wrap up conic sections by looking at some alternative ways of expressing conic equations. And in fact, we're looking at other ways of expressing equations in general. So one of the ways that we're going to look at expressing these functions, these equations, these relationships, other than what we have so far, is something called parametric. And what parametric means is you're describing each piece separately. Rather than having a function that relates x to y, we're going to come up with a function that gives us the value of x and the value of y separately. So far, we've had equations like, y equals 2x squared minus 8x plus 8. And we've either picked values for x or values for y, and we had to find what the other value was to graph it. Well, that is a standard equation. Parametric equation, the parametric form, would look something like this. X equals t minus 2, and y equals 2t squared. Now we do have to define a range for t. Let's say we're going to go from t equals -3 to 3. Well, let's look at what this looks like. So we can make our table here for x and y. Unfortunately, now we need a third term, which is t. T goes from -3 to 3, so let's start out with -3. If t is -3, x is t minus 2. -3 minus 2 is -5. If t is -3, y is 2t squared, so -3 squared is 9, times 2 is 18. T is -2, -2 minus 2 is -4. -2 squared is 4, times 2 is 8. If t is -1, -1 minus 2 is -3. -1 squared is 1, times 2 is 2. If t is 0, 0 minus 2 is a -2. 0 squared is 0, times 2 is 0. If t is 1, 1 minus 2 is -1. 1 squared is 1, times 2 is 2. If t is 2, 2 minus 2 is 0. Y is going to be 8. If t is 3, 3 minus 2 is 1. Y is going to be 18 again. So if we're looking at a graph, we still have ordered pairs here. This is just the ordered pair x is -5, y is 18. They were defined separately in the equation, but they still come together to make an ordered pair. So -5, 18 is somewhere in there. This one's still the ordered pair. X is -4, y is 8. So -4, 8 is somewhere in there. This is the ordered pair. X is -3, y is 2. -3, 2. This is -2, 0. -1, 2. 0, 8. And 1, 18. Now we can see this forms just a simple parabola. This actually is the same equation as I defined up here. Y equals 2x squared minus 8x plus 8. Now, if this were in that equation, I would have done what I just did here, is I would have put arrows on both ends. But since this is a parametric equation, I'm not quite going to do it that way. What I'm going to do is going to look like this. I'm going to put an arrow along it, actually several arrows along it, pointing in the direction of increasing t. Because we only wanted the range, it's only defined on that range from t is -3 to +3, so it doesn't necessarily keep going in both directions. In fact, I really shouldn't have the arrow at the very end here. I should have it back a ways. Like that. So I should have a dot on the end so we know that it terminates there. That's as far as we're defined for, because that's our range given on t. But the arrows tell us that's the increasing t goes in that direction. So for the values of t in our acceptable range, we start here and we go to here. Well, let's look at some other examples of parametric equations. Let's look at, one is a little more interesting. X equals the square root of t. Y equals 1/2 t minus 2. For, now obviously since x is the square root of t, t can't be negative here. So t has to go from 0, let's go to 9. Now I am going to pick values here for t on that range of 0 to 9 that I know are going to give me nice easy square roots. So I'm going to do 0, 1, 4, and 9 because I know those are the perfect squares. So the square root of 0 is 0. 1/2 times 0 is 0, minus 2 is -2. For x, the square root of 1 is 1. 1/2 times 1 is 1/2, minus 2 is -1.5. For 4, the square root of 4 is 2. For y, 1/2 times 4 is 2, minus 2 is 0. For 9, for x, the square root of 9 is 3. For y, 1/2 times 9 is 4.5, minus 2 is +2.5. So we have ordered pairs here. X is only positive. So this is the ordered pair 0, -2, right there. 1, -1.5, right there. 2, 0. And 3, 2.5. So it's looking like that. Now again, I have to stop there, and I'll put arrows on it indicating the direction of the increasing t. So, how can we take one of these parametric equations and convert it back into one of our standard equations that we're used to working with? Well, it's actually relatively simple. I can start out with something like x equals 7 minus 4t, and y equals 5 plus 6t as my parametricized equation. And I can convert this into a standard equation. In other words, it's called eliminating the parameter. In many cases, by quite simply solving one of them for t. So I'm going to start with x here. Let's take that one and solve that for t. So x equals 7 minus 4t. I'm going to go ahead and I'm going to subtract the 7. So x minus 7 equals a negative 4t. And then we'll divide by the negative 4. So x divided by negative 4 is a negative 1/4 x. Negative 7 divided by negative 4 is a positive 7/4. Of course, that equals t. Once we've solved one of them for t, we substitute in the other equation. So that other equation was y equals 5 plus 6t. Well, that's going to become y equals 5 plus 6 times what this equation gave us for t, negative 1/4 x plus 7/4. And of course, we would want to clean that up a little bit by working it out. Y equals 5 plus 6 times negative 1/4 is negative 3/2 x. 6 times 7/4 is 42/4, or 20 1/2. Oops, sorry, 10 1/2, I should say. And then we can combine the 5 and the 10 1/2. So we have y equals negative 3/2 x plus 15 1/2. So there is our non-parametric equation. We've eliminated the parameter, and we can see that that is a simple linear equation. Well, not all of our parametric equations can be solved quite so simply. One other method that we might use, especially if they contain, if the parametric equation contains trig functions. we can turn them into some of our common trig identities. The one we're going to use today, because we're not going to get real deep into the parametric equations, we're going to use sine squared theta plus cosine squared of theta equals 1. Now, let's keep that identity off to the side, and let's look at a set of parametric equations. For example, we might have x equals 4 sine t, and y equals 2 cosine t. In order to substitute these into this trig identity, I have to isolate sine and cosine. So I'm going to solve this one for sine by dividing by 4 on both sides. So I have x over 4 equals sine t. This one I'm going to do the same thing by dividing by 2 on both sides to get y over 2 equals cosine t. And now I'm going to, for each of these, I'm going to square both sides. So x over 4 squared is going to be x squared over 16 equals sine of t all squared, or sine squared of t. Over here, if I square both sides, y over 2 squared is y squared over 4 equals cosine squared of t. And now I can substitute them into this trig identity up here. Sine squared is going to be x squared over 16. Plus cosine squared, we saw down here, is y squared over 4. And that equals 1. Now, you might recognize this from the last couple weeks. That is the standard form of an ellipse. So by removing the parameter, we see what form of an equation that gives us. Well, let's look at some other equations that we might have. Let's say we have x equals 3 plus 2 cosine t, and y equals negative 1 plus 2 sine t. I would like to remove the parameters there. Again, I'm going to solve this for cosine t, and I'm going to solve this one for sine t. Let's work with the x equation here first. So to get cosine t by itself, I first subtract 3 from both sides. X minus 3 equals 2 cosine t. Then I have to divide by 2. So what I have here is x minus 3 over 2 equals cosine of t. We are going to have to square that at some point. So let's do that right now as well. I'm going to leave the x minus 3 squared as just x minus 3 squared. But I will square the 2 to make it 4 equals cosine squared of t. Now let's do the same thing with our equation for y. So to solve that for sine, I'm going to add 1 to both sides. So I have y plus 1 equals 2 sine t. And we'll divide by the 2. So y plus 1 all over 2 equals sine of t. And again, I'm going to have to square that to get sine squared. So let's do that. The y plus 1 squared, just like I did with the x, I'm going to leave that as y plus 1 squared, but I am going to square the 2 to make it a 4 equals sine squared of t. Now, substituting that into sine squared plus cosine squared equals 1, or cosine squared plus sine squared equals 1, whichever way you prefer to do it. I've got the x minus 3 squared over 4 plus y plus 1 squared over 4 equals 1. Now, since these numbers are the same, that tells us, this is the form of an ellipse. But since those numbers are the same, a and b are both the same, this is actually a circle. So if I multiply by 4 all the way through here, I get the equation x minus 3 squared plus y plus 1 squared equals 4. So it's telling us that is a circle with its center at 3, -1. So right there. And a radius, r squared here is 4, so r is 2. So there's our circle. Now that was a circle because of a couple of things. One is it was that form, one was sine squared, one was x squared. But the standard form, parametricized form of a circle will be x equals h plus r cosine t, and y equals k plus r sine t. And you'll notice in the equations I gave you up above, it was x equals 3 plus 2 cosine t, and y equals -1 plus 2 sine t. So I could just take this as a direct translation, that h is 3, so that's x minus 3 squared, and y -1, so that's y plus 1 squared, and r is 2, so r squared is going to be 4. So that translates directly into that circular equation. So again, this form of a parametric equation will always be a circle. The key is those two numbers. In this case, it was the 2, have to be the same. So with that said, it makes sense that the ellipse is going to be very similar to that, only those two numbers are different. So instead of r in both of those cases, we have a and b, where a is the semi-horizontal axis and b is the semi-vertical axis, giving us an ellipse. So knowing that, I could take an equation like x equals -2 plus 3 cosine t, and y equals 1 plus 5 sine t. I could actually write the elliptical equation from that. Or I could actually graph it. If I wanted to just flat out graph that, my center is going to be at -2, 1. Sorry, it's going to be at +2, that's right, -2, 1. So -2, 1 right there. That's my center. The semi-horizontal axis is going to be 3. Since that's the x, I'm going to go 3 units to each side in the x. Semi-vertical axis is going to be 5. So I go down 1, 2, 3, 4, 5, up 1, 2, 3, 4, 5. And there's the limits of my ellipse, like that. Now I could find my center here. Remember, b squared minus a squared equals c squared. So this would be 5 squared minus 3 squared equals c squared. 25 minus 9 is 16 equals c squared. So c is 4. So my foci would be right there. If we went through the conversions, this should be of the form x plus 2 over 3 squared is 9 plus y minus x plus 2 squared, y minus 1 squared over 5 squared is 25 equals 1. If we want to confirm that, let's go ahead and do it. If I solve this for x, this is going to be x plus 2 over 3 equals cosine t. So squared, that'll be x plus 2 squared over 9 equals cosine squared t. This one over here, if I solve it for t, that's going to be y minus 1 over 5 equals sine of t. Squaring that, I will get, y minus 1 squared over 5 squared is 25 equals sine square root of t. And you can see right there, I'm going to substitute this in as sine, sorry, it's cosine, this in as sine. Cosine squared plus sine squared equals 1. There is my elliptical equation. So we've seen the parametric equations for a circle and for an ellipse. Let's look at what it's going to look like for a hyperbola. For a hyperbola, x equals h plus a secant of t, and y equals k plus b tangent of t, where again, h and k are the coordinates of our center, a and b are the horizontal semi-axis and vertical semi-axis. The trig identity we're using here is no longer sine squared plus cosine squared equals 1. What we're using here is the one that is 1 plus tangent squared equals secant squared of theta. But we're rewriting it so it is like this of so you're trying to get the term the way I want this one written. Yeah. 1 is equal to secant squared of theta minus tangent squared of theta. So in this case, the direction of opening of this hyperbola depends on which one is secant and which one's tangent. So the tangent and secant can change places in these equations. Whichever one the secant is with, that's going to be the direction of opening. So since the secant's with the x here, this would be opening horizontally. If it were the other way around, if the secant were with the y, so if it were x were h plus a tangent t, and y is k plus b secant t, that one then would be opening vertically, up and down. So let's do an example of a hyperbolic equation. So let's take x equals -3 plus, I'm going to keep this simple on myself, plus 4 secant t, and y equals 1 plus 3 tangent t. I'm going to solve each of these for secant or tangent. I'm going to solve this one for secant. I'm going to add 3 and divide by 4. Now I'm going to skip some steps in the algebra. I'm assuming you guys can follow. So if I add 3 and then divide by 4, I've got x plus 3 over 4 equals the secant of t. Then when I square that, that's x plus 3 squared over 4 squared is 16 equals the secant squared of t. Over here for y, I'm going to do the same thing. Subtracting 1 and dividing by 3 gives me y minus 1 over 3 equals tangent of t. Squaring that then, y minus 1 squared over 9 equals tangent squared of t. And then placing that into secant squared minus tangent squared. So secant squared is this, so it's x plus 3 squared over 16 minus tangent squared will be the y minus 1 squared over 9 equals 1. I get that hyperbolic equation. So I have a center here at -3, +1. That's my center. Square root of 16 is 4, so I go 1, 2, 3, 4, 1, 2, 3, 4 in either direction horizontally. Square root of 9 is 3, so I go up 1, 2, 3 and down 1, 2, 3. I use that to create my rectangle. And remember, that is used to create asymptotes and since the x is the positive one here, I know the vertex of my hyperbola is on the edges and it goes out towards those asymptotes here. And there's a vertex here going out towards those asymptotes like that. And that is my hyperbola. I could find my focus, my foci, I should say. A squared plus b squared, 16 plus 9 equals c squared. Remember, a is technically 4 and b is 3. So a squared is 16, b squared is 9. So 25 equals c squared, telling me that 5 equals c. So my focus is right here, one more unit out in the horizontal direction. What if I want to form a line? We've already seen, by the way, a parabola. We actually saw that up above where x equals t and y equals t squared. And we could do all sorts of other things with it. We can add, subtract, multiply, divide to make it open up, down. I can do t, this would be plus h here, and this would be plus k there to move it up and down. Looking at the equation for a line. Well, let's take a parametric equation of the form. If the line goes through the points A, B, and CD, the parametric form of that equation, x is going to be equal to A plus t times c minus a, and y equals b plus t times d minus b. And what this is a starting point for x, and this is the rate of change of x. This is the starting point for y, and that's the rate of change for y. Okay, it is 10:21, so it's time for a break. So let's go ahead and take a little bit. We'll come back at 10:30, and we'll start up with polar coordinates. So that was one way of expressing our functions and our equations differently than our standard form. Next, we're going to look at a completely different form of graphing altogether. What we've looked at so far, the Cartesian or rectangular coordinate system, have looked at describing a horizontal and a vertical distance from a starting point. And of course, that starting point was the origin. So everything in a rectangular coordinate system starts from the origin. And if I give you a point, 3, 7, that means that from that origin, we go over 3 units, horizontally 3 units, and then vertically 7 units, that's our point. Well, the other way of graphing points still evolves around an origin. But it goes back to that unit circle we discussed a couple weeks ago with finding trig functions. So that's our origin. But instead of having horizontal and vertical coordinates, we have directions. This is the 0 degrees direction, and the angles wrap around going counterclockwise. So that'd be 90 degrees, 180 degrees, or 270 degrees, and then this would be back at 360. Or if you were looking at radians, this would be 0 radians, pi over 2 radians up here, pi radians, and 3 pi over 2 or 3 over 2 pi radians here. And everything is measured from the origin, but not as a horizontal and vertical distance, but as just strictly a distance and an angle for that distance. So that same point from over here that we located at 3, 7 is going to be located using a distance from the origin and an angle. So we have theta, and that distance is usually referred to as r. So to find the polar coordinate for a rectangular point, so let's say we've got that point from up above, 3, 7. We find r. R is going to be found by simply using that Pythagorean relationship. R squared equals x squared plus y squared. So here we've got r squared equals 3 squared plus 7 squared. 3 squared is 9, 7 squared is 49, adding up to 58. So r squared is 58, or r equals the square root of 58. That square root of 58, we could actually calculate it out to get 7.7 or whatever it is, but it's more accurate to leave it as just simply the square root of 58. Cannot be reduced in radical form any more than that. The angle then, theta, is simply the inverse tangent of y over x, given that it's in the first quadrant. If it's in a different quadrant, we have to use reference angles to find that. So here, this is going to be the inverse tangent of 7 over 3. Which will be 66.8 degrees, 0.80. Typically, I'll go to 2 decimal places on angles, or we'll go to radians. So we converted that point 3, 7 up here from our rectangular graph on the polar coordinate system. It was r is the square root of 58, and theta was 66.8 degrees. Again, often that theta is listed in radians, but I don't have it in radians right now, I have it in degrees. So we converted a rectangular point into polar coordinates. Let's go the other direction. Let's take a polar coordinate and convert it into a rectangular point. So let's take the point r equals 4, theta equals 30 degrees in polar form, and let's convert it into rectangular form. To find x, it is going to be r times cosine of theta. So here that's going to be 4 times the cosine of 30 is the square root of 3 over 2. So that'll be 2 times the square root of 3. The y coordinate will be r times the sine of theta. So that'll be 5 times the sine of, 4, I should say, times the sine of 30 degrees is 1/2, so that's simply going to be 2. So this is a polar coordinate here, would be 2 square roots, or sorry, as a rectangular coordinate would be 2 square roots of 3, comma 2 would be the xy coordinate for that point, for 30 degrees. Well, let's look at converting complete equations. If I have an equation in standard form, and I want to convert it into polar form, let's start out with a relatively simple one, like 3x plus 2y equals 7. Well, remember, x equals r cosine theta, and y equals r sine theta. So we can just simply substitute. X is going to be r cosine theta, and y is going to be r sine theta. Now we don't know r and theta, but we can solve. Let's solve this for r. So what I'm going to do is I'm going to factor r out of this. R times 3 cosine theta plus 2 sine theta equals 7. And then I'm going to divide by the 3 cosine theta plus 2 sine theta. And I end up with r equals 7 over 3 cosine theta plus 2 sine theta. And that is generally how a polar equation is given, is instead of y equals like our rectangular equations are, it's r equals. R is given as a function of theta. Let's take something like our equation for a circle. X plus 1 squared plus y minus 2 squared equals 1. Well, we would make that same substitution. X equals r cosine theta plus 1 squared. Y equals r sine theta minus 2 squared equals 1. And we could solve this and rearrange it solving for r. Now here we're going to end up with r squared in this equation. So this is going to get more complex, but in this case, this is a valid polar equation right here in that form. If we wanted to go through the algebra to solve for r, we're going to end up with actually several possibilities for that equation. There are actually more than one possible values for r there based on that equation. It's going to be quadratic. Well, let's get back to the task at hand, which is graphing conic sections. Our conic sections, we've looked at foci and directrix for the parabola, but when we're in polar form, rather than having multiple foci and the asymptotes for the hyperbolas and stuff like that, what we have is we simply have all conic sections have one focus and one directrix. Like I said, in standard form, we were used to using the focus and the directrix for a parabola. You had the directrix here, the focus here, the parabola opened away from that directrix. But in polar form, all of our conic sections have a directrix and a focus. Let's just use this picture here. Every point on this curve, in this case, the curve of a parabola, I'm going to label those points P. I'm going to label the focus point F and the point on the directrix point D. If I pick a point on that conic section, on that curve, there is a distance from that point to the focus and a distance from that point to the directrix. So the distance from that point to the focus, I am going to label as PF, point to focus. The distance from that point to the directrix, I'm going to label PD, point to directrix. And the ratio of the distance from that point to the focus and the point to directrix is equal to, it's called the eccentricity of that equation. Oops, I got that wrong. It should be point to focus, focus to directrix. Like that. So that eccentricity describes for us not only how the conic section is formed, but how just a second. My eyes got blurry on me for a second there. It describes not only how that conic section looks and forms, it tells us what conic section is formed by that. And I did have that right. That is point to directrix, sorry. Time to switch up my contacts. My eyes are getting really blurry on me. I'm apologizing. I can't read what's on my paper. Okay. So let's take a look at that. That eccentricity, again, from the focus to that point on the graph, or from the directrix to that point on the graph, gives us that ratio. If that eccentricity is equal to 1, it's a parabola. If that eccentricity is bigger than 1, so E is greater than 1, then that graph is going to be a hyperbola. If that eccentricity is less than 1, then it is an ellipse. Think about what this is saying. This is saying the eccentricity equals 1. That's saying the distance from the focus to the graph is the same as the distance from the directrix to the graph. So what does that mean? Well, this point right here, let's pick. The distance from the focus to that point is the same as the distance from the directrix to that point. Remember, from a line, we always measure the right angle. For the hyperbola, that is saying that the distance from the focus to the point is bigger, always larger than the distance from the directrix to that point. And for the ellipse, that's saying that point is always closer to the focus than it is to the directrix. Well, when we're in polar equations, there is a standard form for our conic sections. If our conic sections open horizontally, in other words, they're transverse or major axis, is horizontal. The equations use cosine in them. So it could be of the form r equals EP. Actually, it's not a p, that's a rho technically. Rho is the Greek letter rho. It looks a lot like a p. Over 1 plus e cosine theta. Now, because this is a plus here, that is telling us that the directrix is to the positive side of the focus. So in other words, the directrix is to the right of the focus. Or we might have the form r equals e rho over 1 minus e cosine theta. Because that is a minus there instead of a plus. That's saying the directrix is on the negative side of the focus. Directrix is to the left of the focus. If our major axis or transverse axis is vertical, we use sine in that formula. So that formula could be r equals e p over 1 plus e sine theta. Again, that's a plus. So that's telling us that the directrix is on the positive side of the focus. Directrix is above the focus. Or we might have r equals EP over 1 minus e sine theta. Since that's a minus, this is saying the directrix is below the focus. You'll notice, however, in all 4 forms of that equation, it's EP over 1 plus or minus E times either sine or cosine of theta. So if we're going to look at trying to graph a conic section in polar form, one of the first things we have to do is get it into that form. So for example, if we have R equals, I want to make life easy on myself here, 8 over 4 plus 2 cosine theta. The key to this form of equation for a conic, let's scroll back up here. You'll notice all of these had a 1 in that position. These two as well. So what I'm going to do is in this equation, I'm going to make that a 1 in that position. Since it's a 4 right now, to turn it into a 1, I have to divide numerator and denominator by 4. So what that's going to give me is R equals 8 divided by 4 is 2 over 4 divided by 4 is 1 plus 2 divided by 4 is 1/2 cosine theta. Now that we have it in that form, there are two things we can read off. One is, that's a cosine. It tells us it's going to be horizontal for our transverse or major axis. 2, this is a plus, telling me that the directrix is on the right side of the focus. 3, E equals 1/2. Since that is less than 1, this forms an ellipse. So, all we have left is that 2 up there. What does that 2 stand for? That's EP equals 2. Well, if E is 1/2, EP is 1/2 times P equals 2. Dividing by 1/2 gives us P equals 4. So the question is, what does P tell us? P or rho, however you want to describe it. Well, P is the distance from the focus to the directrix. So that's this distance right here is P. So it's 4 units. Now with this form of a conic section, one of the things that makes it so handy is the vertex is the focus. The vertex is what we refer to as the origin. So if I'm looking at my axes here, my focus is right here. P is 4, which means I go over 1, 2, 3, 4. There's my directrix. Now, E, my eccentricity, is equal to 1/2. What that means is the distance from the focus to a point, or point to the focus, is equal to 1/2 of the distance from that point to the directrix. What I have right here is I have 4 units between the focus and directrix. So I know that PF plus PD equals 4 units for whatever point is right in between here. I'm looking for a point right on that axis there. Well, 1/2 PD is equal to PF. So I'm going to put that in there for PF. So 1/2 PD plus PD equals 4. So doing the algebra here, I get 3/2 PD equals 4. Dividing by 3/2, I get that PD equals 8/3, which means PF equals 4/3. So what does that mean? Well, this point here that I was looking for, I'm going to take that out of there, is going to be right here. That's 4/3 from the focus. And 4 minus 4/3 leaves me with 8/3 from the directrix. So that is a point on that line. Now, other points I can find here, let's find a point vertically going up this what would be the y-axis. I know that any point on that axis is 4 units from the directrix, because the directrix is defined to be 4 units to the right. So if the eccentricity is 1/2, 4 times 1/2 is 2 units from the focus. So 2 units from the focus would be right there. That is another point on my ellipse. Same going down, 2 units down, right there is a point on my ellipse. Let's go over here. Well, I know that whatever distance it is from my focus to that point, I'm just going to label that distance x for now, just for simplicity. This distance here is 4. So x plus 4 has to be equal to 2x. Whatever distance is from the focus to that point, it'll be 4 more units to the directrix. But the distance from the directrix to that point has to be double the distance from the focus to that point. So if I solve this, subtracting x from both sides, I get 4 equals x. So that's telling me I have to go 4 units this way to find the point that's on that ellipse. So there's my next point on the ellipse. So there it is. The ellipse. So I've graphed that from the polar equation. Now let's look at some other polar equations. Let's do r equals 4 over 2 minus 2 cosine theta. So now again, we're worried about this one right here, that value. That is 2, so to make it a 1, you divide by 2 in the numerator and denominator. So this is going to become r equals 4 divided by 2 is 2. 2 divided by 2 is 1. 2 divided by 2 is 1 again. So that becomes 2 over 1 minus cosine theta. Now again, we make sure we know what this equation is going to look like as a graph. First of all, this here, our eccentricity, E equals 1, tells us this is a parabola. Cosine tells us that this is horizontal, and that this is a minus, tells us that the directrix is to the left of the focus. So we're going to have a parabola that opens something like that. A little straighter, but you get the picture. P, we still have to solve for P. We know that EP equals 2, and we know that the eccentricity is 1, so 1 times P equals 2, telling us that P equals 2. So the distance from our focus to that directrix is 2 units. So let's graph it. Here's our axis. And of course, our focus is at that origin, at the vertex. The directrix is to the left, and P is 2. The distance from the focus to the directrix is 2 units. So there's my directrix. 2 units to the left. Now, the eccentricity equals 1, so that means the distance from the focus to a point and the directrix to the point is the same, which means this point here is exactly in between the focus and the directrix. If I go up this way, the distance up from the focus has to be the same as the distance from the directrix. Knowing that the directrix is 2 units away means that from the focus we have to be 2 units away. Same down here. From the focus we have to be 2 units away. And there is our basic parabola. So as you can see, it's actually relatively simple to graph these from polar form. Again, we're not getting fancy here. We're keeping the focus at the origin of the polar graph, the vertex of the polar graph. Simply because I don't want to muddy the waters. I don't want to take another 2 weeks dealing with conic sections in polar form. Let's look at another one here. One more example, and then we'll probably call it. R is equal to, let's do 8 over 2 minus 4 cosine theta. I'm going to give you guys about a minute to put that in our standard form. In other words, get it to where we can find E and P from that equation and find E and P from that equation. So I'm going to give you about a minute to do that. Find E and P. So if we get this in our common form, this is a 2 here, so we're going to have to divide both the numerator and denominator by 2. So R equals 4 over 1 minus 2 cosine theta. So this is telling us that E is right here, E equals 2, or eccentricity is 2. This is saying EP equals 4, E is 2, so P is also 2. Other information then to complete the graph here. Cosine tells us that this is horizontal. Our major axis or transverse axis is horizontal. And the minus tells us the directrix is on the negative side of the focus. So it's going to look like that. So let's set up our axes here. Our focus is going to be at that vertex again. P is the distance from the focus to the vertex. That's 2 units away. So our directrix is right here. Now the eccentricity of 2, that is larger than 1. Since that is larger than 1, that is telling us that this is going to be in hyperbola. And the distance from the focus to a point on the graph is double the distance. So focus to point is equal to 2 times the distance from directrix to the point. Focus to point plus, if I'm looking at just on the axis here, the distance from of the focus to the point plus the distance of the directrix to the point equals 2 units, because there's only 2 units between the focus and the directrix there. If I substitute in that FP is 2 times dP, I get 2 dP plus dP equals 2. In other words, 3 dp equals 2. Dividing by 3 tells us dp equals 2/3. So the distance from the directrix to that point is 2/3. FP, focus to the point, would be double that, would be 4/3. So this distance here is 2/3 of a unit. This distance here is 4/3 of a unit. That is one of the vertices of our hyperbola. Now, as I go up here, going in this direction, I know that the distance from the focus to that point has to be double the distance from the directrix. Well, from the directrix to that point is going to be 2 units. So from the focus to that point has to be double that, or 4 units. It's going to give us a point up here, 4 units above. And of course, going down, it'll be the same thing, 4 units below the vertex. So those are points on our hyperbola. But now a hyperbola has 2 curves to it. To find the second curve, to find a point over here on the left side of the directrix, because there has to be points over here, we again use that fact that the distance to the focal point is double the distance to the directrix for any point. Well, and I know that whatever the distance is, dp here, the FP from the focus to that point is going to be dp plus 2. This is 2 units here. So that is dp plus 2. But that also has to be 2 times dp. So 2 times dp has to equal dp plus 2. So I solve that, I subtract for dp. I get that dp equals 2. So this from the directrix over to here has to be 2 units. You'll see, so I'll put my red point there. This is 2 units, and this is 4 units. So it is twice as far from the focus as it is from the directrix. Now, if I go up in this direction in any way, I know that we have to mirror the other side here. So if I go over 4/3 of a unit from that point, which is how far it is to the focus, this would be the other focus. If I go straight up, I have to be 4 units up from that. And 4 units down from that to get other points on that hyperbola. Again, that's just mirroring the other side. It's 4/3 from that point to the focus. It has to be 4/3 here from that point to where the other focus would be. Points are 4 units up from the focus and 4 units down from the focus. Same here, 4 units up and 4 units down. And we have the other half of our hyperbola. Something like that. So I realize that what we have done today is quite a mouthful. We covered a lot. The good news is we are done with conic sections. We're going to move on for the next 4 classes. We have 4 more lectures left in the class. And we're going to talk about sequences and series and uses of sequences and series, which is actually quite a powerful tool. When you get into calculus, often if you break a function down into its equivalent sequence, it's easier to integrate or differentiate the individual terms of a sequence than it is the larger function itself. So anyway, we have an old homework on the material from last Monday that is due tomorrow. We have new homework on the material from today. that'll be due Thursday. And if you get done with those, there is a quiz on that material. It'll be due Friday. So that quiz for Friday will contain material on rotation of axes and then on these parametric and polar coordinates and equations. That quiz, by the way, I consider to be the toughest quiz of the course. Just giving you a little fair warning. It can't get any worse from there. And do remember, you do get to drop your worst quiz grade. Okay, looking at the syllabus, I can't remember for this class if it's your worst 1 or 2 quiz grades for the semester. But give it a shot. The worst, the worst you can do is try. Anyway, I'm fully anticipating having questions on this stuff on Friday. So come in on Friday. If you have questions on the homework, please write them down. Also, please do not hesitate to use that Ask My Instructor button in my math lab, on the homework at least. You won't have that for the quiz, but please feel free to send me that, those questions. That allows me to see the exact question you're working on. Otherwise, if you come to class and say I had a problem on number 8, when I look in my math lab, my number 8 might look different than your number 8. So if you use that Ask My Instructor button, you can send me the exact question, and I can try to help you out through email or even make a recording like this for you to help you out. Or at the very least, we'll do that at the beginning of class on Wednesday. Anybody have any questions today? Okay. Well, you guys have a great day, and we will see you all on Wednesday.